Okay, so for today what we want to get into for our oil heat lesson is getting into the ignition systems of your oil burners. Now it's really important to know what the ignition system does for an oil burner and really what it consists of. So today we really have two main components of the ignition system on an oil burner that we are going to primarily deal with pretty much on a daily basis. That is your ignition transformer and your solid state igniter. Now, some people may ask, well, how come the electrode isn't in this presentation? Well, because the electrode really is another component that kind of like deserves its own separate talking point, I guess you might want to say. So for this lesson here, what we really are just going to really concentrate on is just the two types of transformers and the ignition that these two can actually give us. So the ignition transformer really is nothing more than a step-up transformer that uses copper windings around an iron core. So what it really is doing, it's taking 120 volts, which is supplied to it through, for here, right, these two black wires, which is our primary winding. And it's going to step up that voltage to an output voltage of around 10,000 volts. Now that 10,000 volts is going to come out of these two springs right here. These two springs is what actually sits on the electrodes and sends that spark down so that we can ignite the oil. So it's really important to kind of look at the nameplate on the ignition transformer to see what type of secondary voltage you're dealing with, and also looking at the volt amps and milliamps ratings on there, and I will discuss that in a minute. So really how it's using this voltage and stepping it up to 10,000 volts, it's accomplished by pretty much like a 90-to-1 winding ratio between the primary and secondary winding that's wrapped around that iron core. So the solid state igniter utilizes electronics, so it's a little bit different than your ignition transformer. It puts an output voltage of anywhere between 14 to even 20,000 volts. I'm not exactly 100% sure, but I do believe that there are some solid-state igniters that actually may put out even more than 20,000 volts of electricity. But however you look at it, both of these components are going to supply a high voltage electricity to those electrodes. So it's really what's important to know is that we need that amount of voltage to send down to the electrode tips so that we can create an electrical arc, which will then in turn ignite the atomized oil. So burners use two types of ignition control systems. That's your interrupted ignition and your intermittent ignition. Interrupted ignition is the type of ignition that has the spark on only for a short period of time at the beginning of each burner operating cycle, and then it's going to turn off once the flame is established. Intermittent, on the other hand, the spark has to be on as long as the burner is running, so it's running all the time. Intermittent ignition used to be called constant ignition, and some manufacturers call intermittent ignition constant duty ignition. So don't get them confused. So you need to make sure that you understand that interrupted ignition means that the spark is going to be on for a short period of time only to ignite the oil, and then it's going to shut off. Intermittent ignition means that the spark that is being generated is on all the time as long as the burner is operating. So intermittent ignition, though, however, is actually the better of of the two. And the reason why that is because having the spark on all the time during the run cycle, it's going to reduce system performance. It's going to put a lot of wear and tear on the parts in the oil burner, especially the electrodes. The electrodes are going to, life expectancy is going to be reduced. The igniter and ignition transformer, because it's being used a lot more than what it really needs to be, is going to also reduce. You're going to use a lot more electricity to keep the burner running, and obviously it could be a little bit more noisy because of the fact that it's actually on all the time. Intermittent ignition, though, it may hide combustion problems that can cause sooting or soot plug the boiler in operation and furnaces and other stuff like that. So we constantly seem to see a lot more manufacturers going towards the interrupted ignition, simply due to the fact is that we want to only use these parts when we need them to be operating. Okay, the constant arc of intermittent ignition, though, also keeps the flame burning, even if the system is smoking and sooting up and leaving unburned oil in the chamber. With interrupted ignition, a poor flame goes out and the unit goes on safety. Nitric oxide or NOx emissions are higher with intermittent ignition because the spark burns nitrogen. So it's really important to make sure that we have a spark, and it's really important to make sure that we have a spark that is strong enough so that we can actually ignite the oil. Because remember, the spark across the electrode gap at the tip of the electrode must be strong enough to withstand the velocity of the air being blown through the air tube by the burner fan. Okay, the air being blown through the air tube forces the ignition spark to form in an arc toward the oil spray. So really what we're trying to do is we want to use the air that's coming down the air tube to almost push that spark into that spray of oil so that we can actually ignite it. So that arc extends into the spray, causing the oil vapors to ignite, and therefore you're going to have a flame. So the ignition voltage must be high enough to create a spark that is hot enough to ignite that oil. So how do we get that heat? Is by applying the correct amount of voltage needed to do it. So widening the spark sometimes will produce better ignition. It all depends on the burner. It depends on the type of ignition system that you're dealing with. But always remember one thing, is that you're dealing with high voltage. You're dealing with 10,000 to 20,000 volts of electricity. So you have to be very, very careful. Okay, so depending on the size of the person, contact area and time, and the voltage characteristics, the magnitude, frequency, and path, electric shock can occur and cause bodily damage, burns, or death. So you need to be very, very careful and use caution when you are troubleshooting the input and output ends of an ignition transformer. So if you must replace a transformer on an oil burner, you have to make sure that you know a couple of the facts that go along with them. First off, you have to know the size of the mounting base and the location of the mounting holes. You have to make sure you know the position of the high tension terminals, the style of the transformer, high tension clips, if there are any. You need to know the secondary voltage. You need to know the primary voltage. And you also need to know the type of transformer body. Obviously, all of that stuff is on the nameplate, the model, serial number of the burner, model, serial number of the transformer. But you also want to make sure that you have the transformer that's going to match that burner. When it comes to wiring an ignition transformer, wire the ignition transformer to the burner as follows. If you're doing intermittent ignition, all you're going to do is attach the wire from the transformer or igniter to the neutral wire, and the other wire to the orange motor wire from the primary control. Now this is going to apply if you're using the simple 3-wire Honeywell primary control. If you're going to do interrupted ignition, attach one wire from the transformer. You have to obviously make sure that you have a primary control that is built for this purpose. You are going to attach one wire from the transformer or igniter to the neutral wire and the other wire to the ignition wire or terminal on the primary control. Now, one of the drawbacks to iron core ignition transformers is, well, a transformer does exactly what we say it's supposed to do. It transforms voltage. Okay, there is a single copper winding on the primary side for every 90 to 100 windings on the secondary side. And that's how it transforms voltage. So for every 1 volt you remove from the primary side of that transformer, you remove about 90 volts of the secondary side. So the ignition of the atomized oil is not a result of the spark, but rather the result of the heat being generated from the spark. So if I do not have enough voltage coming out of my secondary side, I'm not going to have the correct amount of heat needed to properly atomize and ignite, to properly ignite that oil, because I'm losing the voltage. So you must be able to generate at least 600 to 700 degrees from that spark to ignite number 2 fuel oil. Okay, that translates to approximately about 9,000 volts and about 19 milliamps of short circuit current. Now, most of your ignition transformers, they are set up for 10,000 volts with 23 milliamps of current. Now, that provides a small amount of margin of error for them, but obviously if we start having voltage issues, that can start to create a problem. Now, testing transformers, there's a lot of different methods of doing it, okay? But one thing that you must keep in mind when you are testing these transformers is to make sure that you have the correct input voltage to the primary coil. This is very important because the output of the transformer is relative to the input voltage. So there are several types of transformer testers available. These testers are dependable and usually come in their own carrying case with their own set of instructions. So you must read those instructions carefully to make sure that you're using the tester correctly and it's used for that particular type of transformer. Another test that you can do when it comes to testing an iron core transformer is actually just taking an ohm reading, doing a resistance test across it. So to do that, the first thing that you have to make sure that you are doing is you have to unplug the power, shut the power off to the unit, disconnect the primary leads from that transformer. Okay, now you are going to take a resistance reading across the primary windings. You're going to attach the test leads from your ohm meter to the primary leads of the transformer. Now you should get a reading of about 3 ohms plus or minus 10%. Usually, depending on the manufacturer of the transformer, you could probably get anywhere maybe between 2.5 to maybe 4 ohms of resistance, give or take. Okay, if your readings is high or low, just replace the transformer. Test the secondary side of the transformer. You are going to touch one of your ohm leads to the secondary terminal and the other to a mounting screw or ground. Now you should get a reading of about 12,000 ohms plus or minus 10%, and then perform the same test on the other secondary terminal. You should get a same reading or approximately the same reading. Now again, if they're too high or too low or they vary widely, replace the transformer. This following table here gives you a little breakdown or maybe some guidelines of what you should be reading depending on the type of transformer you're dealing with. So like for Allison on your primary side, you might want to see maybe about 2.4 ohms of resistance. On the secondary side, between each post to ground, you're looking at maybe about 9,200 ohms of resistance. Your solid-state oil burner ignition systems, your electronic ignitors, these are a lot more common today. Reason because they are smaller, they're lightweight, and they have much larger starting power. The output voltage is anywhere, again, between 14,000 and 20,000 volts of electricity, with an amperage reading of anywhere between 16 milliamps and about 45 milliamps on that secondary coil. Okay, anywhere between that, that's considered normal. Now remember, with these types of igniters, they do not have an iron core in there. They're not necessarily two windings wrapped around an iron core like the igniter, your ignition transformer. These are actually printed circuit boards. And what they usually call those printed circuit boards is kind of like a tank mechanism, or that's what they like to refer them to as. So this technology allows the igniter to have a more constant output if the input voltage happens to decrease. So what we're saying there is that if you have a little bit of a voltage spike or you lose some voltage on the primary side, it really doesn't affect that secondary output that's coming out of our output side of these types of guys. It remains relatively constant. Electrical consumption from an igniter is anywhere between 30 to about 50 watts, much less than what an ignition transformer is going to be using. Now, when it comes to testing an electronic igniter, you have to make sure that you keep in the back of your mind, again, that they do not have a primary and secondary winding like the old ignition transformers, but they do have transistors and other stuff in there. So troubleshooting and servicing them should be done to manufacturer's recommendations. When you look at these and you pull them out of the box, read the paper that comes along with them. It tells you how you can service and troubleshoot them. Okay, you do not use a transformer tester to test electronic igniters. They have their own separate way of doing things. So testing electronic igniter systems is different from testing ignition transformers because igniters utilize a high frequency output. The cycling operation of a solid-state ignition system are about 20,000 times per second. A standard AC transformer operates at 60 times per second. So this is the main reason why we cannot test a solid-state igniter with a standard ignition transformer tester. They just operate at a different cycling or a different wavelength. Before you perform any of these tests, again, make sure that you are using manufacturer-approved testing procedures and the correct tools. And be extra careful not to directly short the terminals without a spark being between them. Okay, keep in mind that igniters are not merely a pair of coils, but rather a complex electronic device made of several electronic circuits and components. So the first basic test for igniters is to place an ohm meter across the igniter output terminals with the power off and measure the resistance from each igniter post to ground. The igniter is considered good if the resistance from each post to ground has no more than a 10% difference between the posts. Okay. It's also important that you verify continuity between the igniter case ground and true ground. Another test that is approved by most manufacturers is to bring the igniter output terminals to within a half to maybe 3/4 of an inch apart and then turn the power on. And when you turn the power on, you should get a nice strong blue spark that gets generated across those terminals. Another trick is to let the spark for a few minutes, and that by about 5 to maybe 10 minutes in most cases, and see if the spark changes from a blue to an orange color. If it does, replace it. And finally, you can check both electronic igniters and iron core transformers with a common test. You can bring the igniter or transformer output terminals to within a ½ inch to 3/4 of an inch apart. You can place a milliamp meter in series with the hot line going to the igniter and turn it on. The reading should stay relatively steady and not vary for at least 5 minutes, with a strong blue spark throughout the test while staying within 10% of the rated amperage draw for that device. So in order to transport the high voltage from the secondary terminals of the ignition transformer or solid state igniter, an effective and efficient path must be provided to the ignition electrodes. Okay, and those paths can be a couple different things. They can be ignition cables, they can be bus bars, or they can be the spring type conductors. Now these are the things that you're going to see on the bottom of the ignition transformer or solid state igniter. Now your ignition cables are normally constructed of heavy stranded copper wire covered with heavy insulation to insulate against dampness and ensure transmission around, over, or under any other conducting surfaces between the transformer location and the electrodes. Your bus bar is a non-insulated heavy gauge strip of metal that are made by the oil burner manufacturer to the length and shape to fit a certain model of burners. And then you have your spring clips. Those are similar to your bus bars, except a contact with the transformer is maintained by spring tension, and after some time those clips can lose their tension and prevent proper and desired contact.